Okay, so the last section of the semester is 5.5, which is the substitution rule. And what I'm going to do is I'm going to start this one off just by looking at a really easy example. So if we're given, let's say, the integral of cosine of x dx. Now, real quick, this is called an indefinite integral. All right, and it's indefinite because we are missing our limits of integration. All right, so we call this an indefinite integral. Now, according to our table of integrals, we know that the integral of cosine of x dx is going to be sine of x plus some arbitrary constant. Because remember, when you do the integral of an indefinite integral, you get a family of solutions. Okay, so this represents a family of solutions where this constant is basically the y-intercept, and it's going to either shift the sine curve up or down along the y-axis. If this was a definite integral, then we would definitely know which one of those lines we're talking about, because we would have a starting point and an ending point to find the area underneath that curve. All right, so the question now becomes, well, what is the following integral here? So what is the following? What is the integral of cosine of 2x dx? So notice these two problems, I'll zoom out here. Notice they're extremely similar. The only difference here is that coefficient within the argument of the trigonometric function is not a 1. It's actually a 2. Okay? So if you think about this, all right, you may sit there and guess that you would say, well, maybe this is going to equal 2 sine 2x, okay? And maybe that's because, plus a constant. And maybe that's because if you were to take the derivative of cosine of 2x, you would have to use the chain rule here, and you would come up with 2 sine of 2x. So maybe if you integrate this, then you get back to that. And that is actually not the correct answer. Okay, that is not the correct answer here. Because remember, you're differentiating cosine of 2x, and what we need to do is find that original function that gave us cosine of 2x, not the derivative of cosine of 2x. Okay? So, we're really, really close with our answer here. Okay? We're going to use a technique called U Substitution. Okay, that's the technique we're going to do. All right? And what we're going to do is we're going to let u equal some function of x. Now, when I give you the formal definition, this is going to be a little bit clearer for us to see. Okay? So if we let u equal some function of x, then the derivative of u is going to equal the derivative of the function of x. Okay? Now you may be asking yourself, okay, well, where am I getting this? Well, if I look above, notice inside of the argument of the trigonometric function, inside of cosine of x, or cosine, I have 2x. I have a function of x. And then outside, and let me go ahead and use a different color here to highlight. That dx there stands for the change in x. It's the derivative of x, okay? So what we're going to do here is we're going to let u equal 2x, which is our function of x here. And the derivative of u, the derivative of 2, is going to be, the derivative of 2x is going to be 2 times dx. In other words, times its differential. Okay? In fact, technically, here's what it really is. Okay? I kind of cheated there a little bit. We know u is a function of u is a function of x. So it's really u of x equals 2x, okay? Now, if I were to differentiate this, I have to do this implicitly. Because u is the variable, it's the dependent variable. The independent variable is going to be x, so this would be du dx equals 2. However, if I want to solve this for du, I just multiply both sides by dx, and that is how I come up with du equals 2 dx, okay? So if you want to, hopefully now that you understand this intermediate part, you don't have to write that all the time. What you would just write is du equals the derivative times dx, okay? So I'm going to go ahead and just erase this. I'm just going to make this a u again. And then I'm just going to write du equals 2 dx, all right? Now, here's the key to this. Whenever you're using U substitution and you say, okay, I'm going to let u equal this function of x, and then I'm going to differentiate it, you need to find those things within your derivative, okay? I'm sorry, you need to find them within your integral. I'm sorry. So right now, I kind of have this. In other words, I got the 2x. I have that. The issue here is, and this is my thing, all right, is this, we got the dx here. Sorry, I thought I changed that to green. We got a dx. However, we also have this coefficient of 2 in front of it. So what I'm going to do is I'm going to divide both sides by 2. And this is going to give me u equals 2x, and then 1/2 du equals dx. Now, there's a reason why I'm saying this. Notice now, if you look at our problem and you look at our substitutions, we have the 2x, we have dx. And because we can go ahead and we can basically put like little check marks next to that, we're going to go ahead and make the substitutions. So I'm going to rewrite my problem as the integral of cosine of u, and instead of writing dx, which would be next, I'm going to write what dx equals. Dx equals 1/2 times du. Now, we know from our properties of integrals, if we have a constant, so let me highlight our constant in our problem. I'm going to highlight this in, I wish I had a different color here. Yellow. I'm going to highlight it in yellow. So here's our constant. We're going to take that constant and we're going to pull it out front of our integral. So here's what my problem turns into. 1/2 times the integral of cosine of u du. And we know that the integral of cosine is going to be sine. So this is going to be 1/2 times the sine of u plus an arbitrary constant, okay? And then the last thing you want to do is, since I gave you the problem in the variable x, I want the answer in the variable of x. So we need to make a substitution for u, but we've already established that u equals 2x. So for a final solution, we get 1/2 sine of 2x plus c. And that is how we use U substitution. So let me go ahead and let me give you the rule. There we go. So here's what your book has. Okay, so it's Theorem 5.6, and it just says, let u equal some function of x where this function is differentiable on an interval, and let f be continuous on the corresponding range of g. On that interval, you have the following. Okay, now, here's where it gets not crazy, but what we have here is basically we have a composite function. You have f of g of x, okay? Now, we know that if we were to differentiate f of g of x, we would have to use the chain rule in order to do that, okay? So if you look, and I'm going to match this up here. If you look, here's my composite function right here. There's my f of g of x. And then right here in green, well, that is the derivative of the inside function. So the substitution rule allows us to integrate the chain rule, basically. And what we're going to do is we need to be able to find what that inside function is. So you're going to let g of x equal u. Okay? And when it says here where g is differentiable on the open interval, it needs to be differentiable because you need to have, and I'm going to underline this in red, you need to have the derivative of that function times dx within the integral itself. If you have both of those little tools there, or little check marks like I used before, then you can go ahead and use U substitution, okay? And what's nice is they gave us here a little procedure. So, and you can see this is exactly what I did in the previous problem. So the procedure is if you're given an indefinite integral, and this also works for definite integrals, and I'll show you how that works in a little bit. So given an indefinite integral involving a composite function, f of g of x, identify the inner function and let that be equal to u. Then you're going to take the derivative of that and make the appropriate substitutions. And that's step 2, which is you're going to substitute in u and du into the integral. And then you're going to evaluate this new integral with respect to u. Lastly, just make the substitutions back. If I give you the problem in x, I expect an answer in x. If I give it to you in z, I expect it in z. Okay? So there is a disclaimer. Not all integrals yield to the substitution rule. In Calc 2, Calc 2 is basically, I'm going to say 99% of the class. Actually, I'm 95%. Because there are some things that you really don't do, but 95% of the class is integration. That's it. So in Calc 2, you pick up right where we're leaving off here with the substitution rule. And then you're going to learn all these other techniques like integration by parts and trigonometric substitution and partial fraction decomposition. So it all starts right here, though, with the substitution rule. Now, remember, you got to be able to do this. And I'm going to underline in red what I'm about to say. In order for you to use the substitution rule, you have to be able to put a check mark above both of those, meaning g of x and g prime of x has to be in your original problem. It has to be within the integrand in order for you to use U substitution. Okay? So let's go ahead and let's look at some examples. All right, so here's our first example. Make sure I got my black marker here. There we go. So we're going to find the integral of e to the 10x dx. Okay? Now, we looked at a problem similar to this in the previous lecture video. Now I'm going to actually show you how this works. So what we're going to do is we know on the surface the integral of e to the x dx equals e to the x plus some arbitrary constant. Now, the problem is we don't have e to the x. We have e to the 10x. We have this 10 out front. So what we're going to do is we're going to let u equal 10x. And then du is going to equal 10 dx. Okay? Now, it would be nice right now if we can go ahead and use U substitution. Okay? But we're not quite there yet. Because notice, we would need like a 10 down with everything else in order for us to just go ahead and use U substitution right from the start, okay? But what we're going to do is we're going to divide both sides by 10, and that's going to give me U equals 10x, and then 1/10 du equals dx. So now notice I can go ahead and put check marks next to things. I have 10x. All right. In fact, let me go ahead and just highlight. There's 10x. Here's 10x. And then dx. And there's dx. So we're going to go ahead and make the substitutions here. So my problem is going to turn into, so let me just rewrite it. The integral of e to the 10x dx equals the integral of e to the u times 1/10 du, where I'm going to pull the 1/10 out front. And now I can go ahead and integrate. I know the integral of e to the u is going to be e to the u, so we get 1/10 out front times e to the u plus a constant. And then the last move here is just make our substitutions. 1/10 e to the 10x plus c. And there's our problem right there. Now, this very easy, straightforward problem. They do get a little bit more intense. Okay? So let's try another one here. All right, so how about this one? The integral of 2x times the quantity x squared minus 1 to the 99th power dx. Okay? Well, if we go back to the definition, all right, if we go back to that definition of the substitution rule, here's what we have. I'm going to write it in red. The integral of f of g of x times the derivative of g of x dx. So notice, and I'm going to highlight so you can see exactly where everything matches. So x squared minus 1 is going to be the inside of the composite function, so that's g of x. And then outside of it, if you notice, 2x is the derivative of g of x. So you know right now, man, I could use U substitution here, and that's a good feeling. Like, you can see it. It's staring you in the face. So let's go ahead and let's do this. So I'm going to let u equal x squared minus 1. du is going to be 2x dx. Now, we know we got everything we need right now, and it looks good. And I agree with you, okay? Sometimes, though, it's not this easy, all right? And I'm sorry for that. Like I said in the previous video, I wish there was a one-size-fits-all model, and it's not. But we're going to go ahead and just use our U substitution here, because notice we got the x squared minus 1. And then if I just highlight this, we got the 2x dx as well. So this is going to turn out to be the integral of u to the 99th power. And then the 2x dx is going to be replaced with du. So now when I integrate this, I can use the power rule. So I'm going to get u to the 100th power divided by 100 plus an arbitrary constant. And then I'm going to make my last substitution. U equaled x squared minus 1 to the 100th power all over 100 plus c. Okay? Now, here's the beautiful part about this. All you got to do to check yourself to make sure you're correct is differentiate. In other words, if we were to take the derivative of what we have here, so give me 1 second, I'm just going to write it out. So if we were to take the derivative of this, we should get what the original problem was, which is, I forget already, 2x times x squared minus 1 to the 99th power. Is that it? Yep. So let's go ahead and let's do that. Let's show that this actually works. So what I'm going to do is I'm just going to rewrite this real quick to make it look a little bit easier for my eyes. All I did is I just took that, the denominator of 100 and moved it out front. So now when I differentiate, I'm going to get 100 over 100 times the inside, and then multiplied by the derivative of the inside. Remember, it's a chain rule. The derivative of a constant is 0, so I don't have to worry about that. 100 over 100 reduces to 1. If I take the 2x and put it out front, notice I get exactly what I started with, which is exactly what should happen every single time. All right, now our next example here. I promise I'm not throwing you a curveball, all right? But I want to show you where this U substitution, although it looks good, sometimes it breaks down. All right, so here's a problem right here. And this is going to look really, really familiar. The integral of e to the x squared dx. Now, a lot of students would sit there and go, oh, let's go ahead, let's use U substitution because, we can do that here. And what I'm going to do is I'm going to show you, we're going to try to attempt to use it. So we're going to let u equal x squared. Therefore, the derivative of x squared, du, is going to be 2x dx. All right. Now, personally, this is just me. Anytime I see a constant out front, I always move it to the other side. In other words, what I'm going to do here, and I always do this, it is just me, you don't have to, but for me it makes a lot of sense. So I'm just going to divide both sides by 2. So that's going to give me 1/2 du equals x dx. Now, here's the issue. We got u squared. That's a good thing. So I could definitely put a check mark next to that. But the problem is with the second, with this du. Notice this du says x times dx. Now, if you go back to our problem, we got the dx. But there's no x here. And because there is no x, you cannot use U substitution here. Okay? In fact, up until this day, right now, there's no way to solve this problem other than using numerical techniques, which, you can do it by hand. It's going to take you a very long time. Or you can use a computer to basically estimate the area under the curve by using the formal Riemann sum definition that we learned previously. You could do that. And what you would just tell the computer to do is just draw, 1,000, 1,000,000, 10 million different rectangles and then add up all the little areas underneath the curve. And in order for you to do that, you got to know how to program. And you need to know different mathematical techniques. I'm really forcing myself now to remember. I took numerical analysis as an undergraduate, and then I took it as a graduate. I think you can use Simpson's rule, which is a numerical technique. You can use ODE 45 in MATLAB, which is it's a derivative of Simpson's rule. And if you don't know what I'm talking about, all you got to do is just type in Simpson's rule mathematics, and you will see you're going to see a bunch of different websites that can link you to stuff like that. All right, but what it does is it estimates the area under the curve using trapezoids, I think. But anyways, I digress. Let's get back onto this problem. So right now, you can't use U substitution. So you would say, can't use U substitution here. There's no there is no solution to this integral here. Okay? However, with the next example here, I'm going to write it directly underneath. If this is the problem, the integral of x times e to the x dx, well, then you can go ahead and use U substitution. So since we already have the U substitution above, I'm just going to rewrite it. So now my problem turns into the integral of e to the u times, 1/2 du. Because notice here, now I have the x dx in my problem. I'm going to take the 1/2 and pull it out front. And now I can go ahead and integrate. So I get 1/2 e to the u plus a constant. And then since u equaled x squared from my original substitution, I get 1/2 e to the x squared plus c. All right. So I'm gonna do a couple more here, and they're not intense. They look intense, but they're really not. And then what I'm gonna do is I'm gonna show you a couple definite integrals using U substitution. Okay, and like I said, it's very easy. It's the same technique. You got nothing to worry about. So here we go. Here's another one. So we're gonna find the integral of 2x squared over the square root of 1 minus 4x cubed dx, okay? Now, now that we have an idea on how to do this, okay? I'm going to show you some tips and just some techniques that we should get comfortable with doing because it makes our life so much easier. For example, before I even use U substitution, I see this 2. I'm going to rewrite my problem by putting it out front. Because remember, with constants, you can move them out front. That is huge. Now that I kind of have that constant out front, I'm going to look in the numerator. I'm going to look in the denominator. I'm going to say, okay, is one a derivative of the other? Or does it kind of look like it? So if you look here, and I'm going to highlight real quick. If you look there, you have in the numerator x squared, and then in the denominator underneath the radical, you have x to the third. Well, we know the derivative of x to the third is going to be 3x squared. So what I'm going to do here is I'm going to let u equal 1 minus 4x to the third, and then du is going to equal negative 12x to the second dx. Now, I had a professor a long time ago who showed me this, and his name was Mr. McCarthy. Super intelligent guy. And this is when he said, he goes, Floater, here's what you're going to do. When you see this constant out front in your du, just divide both sides by it. Because you're not worried about the constant. What you're worried about is the x squared dx, all right? So if I just go ahead, and I'm going to zoom out here, and I'm just going to rewrite this real fast, and you're going to see what happens. So I have u equals 1 minus 4x cubed. Negative 1/12 du is going to equal x squared dx. What he would say, okay, do you have x squared times dx in your problem? And if you look, and I'm going to go ahead and erase this, so I want you to look right in the middle of your screen up top. That dx is really dx over 1. Notice I totally have x squared times dx. So I know U substitution is going to work. I have what my substitutions are going to be. So I'm just going to rewrite my problem as 2 times the integral. Instead of writing x squared times dx, I'm going to write negative 1/12 du over, and instead of writing the square root of 1 minus 4x cubed, I'm going to write the square root of u. Now, hopefully, you're already seeing my next move. Notice I got a constant right here, so I'm going to pull it out front. So this is going to be negative 2 over 12 times the integral of 1 over the square root of u du. Now we're almost home free. We know that in order to take the integral of 1 over the square root of u, not only do we have to make this square root an exponent because we want to use the power rule, but we're going to have to move it up into the numerator. So with a little simplification, we get negative 1/6, because 2 over 12 is 1/6. So we get negative 1/6 times the integral of u to the negative 1/2 du. Okay? Now, we got it in the form of what we want. It's a nice, easy integral, and we can go ahead and do this. So we get negative 1/6 times. Now remember, and I'm going to do this off to the right-hand side. So I'm going to do this off to the right-hand side. When we take the integral of u to the negative 1/2, we need to add 1, but I'm going to be really clever. I'm going to write 2 over 2. And then we also have to divide by that as well. So negative 1/2 plus 2 is positive 1/2. And then to simplify this, we're just going to multiply by the reciprocal, 2u to the 1/2. So I'm going to take this, and I'm going to just write it over into my answer. So I'm going to scroll back over to the left. So I get 2u to the 1/2 plus a constant. Now let's simplify a little bit more before we make our substitution. Negative 1/6 times 2 is going to be negative 1/3 u to the 1/2 plus c. And then our last move is to substitute in what we let u equal. Well, remember, we let u equal 1 minus 4x cubed. So this is going to be negative 1/3 times the quantity of 1 minus 4x cubed, all raised to the 1/2 power. Okay? Plus c, and there is our solution. Now remember, to check yourself, differentiate your solution. So, let me just write the word check. So we're going to find a derivative of negative 1/3 times 1 minus 4x cubed to the 1/2 power plus c. So I'm just going to speed this up a little bit. So our derivative is going to equal, well, we pull the 1/2 out front. So we get negative 1/3 times 1/2 times 1 minus 4x to the third, all raised to the negative 1/2 power, times the derivative of the inside, because this is a chain rule, negative 12x squared, plus the derivative of a constant, which is 0. So now it's just a matter of just cleaning everything up. A negative times a negative is a positive. 3 times 2 is going to be 6, so this is 12 over 6 times 1 minus 4x cubed to the negative 1/2 power times x squared. 12 divided by 6 is 2. So, and I'm going to move this x squared out front. So this is going to be 2x squared times 1 minus 4x cubed to the negative 1/2. And just to clean this up, we don't like negative exponents. I get 2x squared over 1 minus 4x cubed to the 1/2, which is 2x squared all over the square root of 1 minus 4x cubed, which is exactly what the original problem was. Okay? So you can always do this. Just take the derivative. Sometimes the derivatives are not nice. They're not pretty, but there's nothing you can do about it. Okay? But what's nice, you can check yourself. Okay? Let's try another one here. We're going to do the integral of the sine raised to the 10th power of theta times cosine theta d theta. Okay? Now, I do have to make everybody aware of this because I don't know if you know this or not. But anytime you write, like, let's say sine squared theta, you can rewrite that as the sine of theta squared. Okay, that's what that means. So in reality, this problem is really the integral of sine theta to the 10th power times cosine theta d theta. So notice right here is that composite function that we're looking for. What we're hoping is this is our derivative of the inside composite function. So the only way to know is to check it. And I think you can see it, but we're going to do it anyways. So we're going to let u equal sine theta. Du is going to equal cosine theta d theta. Notice I don't have to worry about a constant or anything. There is no constant in front of the cosine of theta, so I don't have to worry about dividing anything. So I have sine theta, check. I have cosine theta d theta, check. We can go ahead and use U substitution. So this is going to be the integral of u to the 10th power times du. It's as simple as that, where this equals u to the 11th over 11 plus a constant, and then make your substitution. U was sine theta, so this is going to be sine theta to the 11th over 11 plus c, or another way you can write this is sine to the 11th theta over 11 plus c. Both are 100% acceptable. Okay? So hopefully by now you can see how this works. Okay? What I'm going to do is I'm going to transition into definite integrals, and I'm going to show you how definite integrals work. And it's actually very interesting how everything just happens to work out. So let's look at this problem here. We're going to do the integral of, or the integral from 0 to 2 of 2x over x squared plus 1 squared dx. So it's similar to one that we did above. Let me write this cleaner. All right, there we go. Okay, now we can't use any of our rules, and what I mean by that is like constant rule, power rule, trig rule, like none of those apply here. Also notice you got a 2 right there, so before I do anything, I'm going to pull the 2 out front and just rewrite this. In our denominator, there's our composite function, x squared plus 1 raised to the 2nd power. So we're going to try to use U substitution. I'm going to tell you it's going to work, but we're going to try it anyways. So we're going to let u equal x squared plus 1. Remember, it's the inside of the composite function. Du, therefore, is going to equal 2x dx. Note that I have a 2 right here, so I'm just going to rewrite this as 1/2 du. I'm going to divide both sides by 2. Let me make that look cleaner. I'm going to divide both sides by 2. And that's going to give me 1/2 du equals x dx. All you got to do now, match things up. I'll go back to my trusty highlighter. X squared plus 1. Got it. X dx. X dx. Got it. So I know I'm going to use U substitution. So let me go ahead and rewrite. And then you're going to see something here. Okay? So I got a 2 out front. Integral of 1 over u to the 2nd multiplied by 1/2 du. Now, before I even go further, I want you to notice that I did not write something. And that something I didn't write were my upper and lower limits of integration. And the reason why I didn't write them is because these limits of integration, I'm going to highlight them in this in yellow. These limits of integration right here, even back in the original problem, they are x values, okay? And what we've done here is we've changed our variable from x into u, all right? So we don't write the limits of integration. Now, there is something we can do, and I'm going to do that at the very end. So I'm going to actually redo this problem. But what I want us to do is just do this problem like we normally would, okay? So for now, we're going to just disregard the upper and lower limits. They're going to come back in a little bit. So just let me go ahead and just erase this. So let's approach this problem like we normally would. Notice right here we have the 1/2, so I'm going to pull it out front. So that's going to give me 2 over 2 times the integral. Now, 1 over u squared, we need to rewrite that as u to the negative 2, because we need it to be an exponent so we can apply our power rule, times du. Now, 2 over 2 simplifies into a 1, so this is nothing more than just u to the negative 2 power times du. So, when we integrate, remember, you're adding 1. I made that mistake the other day. So this is going to give me u to the negative 1 over negative 1. Okay, now I'm not going to put the plus c here because I have a definite integral from the very beginning of the problem. What I'm going to do is I'm going to make my sub. In other words, we let u equal x squared plus 1. So this is going to be negative parenthesis x squared plus 1 to the negative 1, or negative 1 over x squared plus 1. In other words, what I did is I took this and I made it a positive exponent. Notice I'm back in the variable of x. And now I'm going to evaluate this from 0 to 2. Okay? So, my upper limit first, 1 over 2 squared plus 1, minus my lower limit, negative 1 over 0 plus 1. So this is going to give me negative 1 over 2 squared is 4 plus 1 is 5, so this is negative 1/5. Negative and a negative back to back, we know make it a positive. 1 over 1 is 1. So this is just nothing more than just negative 1/5 plus 5 over 5, which equals 4 over 5. Okay? So that is how you use U substitution with definite integrals. All right? All you got to do, and I'm going to zoom out and recap real quick. So, first, let me erase this real quick so you don't get confused. First, what we want to do is we let u equal something, and when we figure out, do we have the derivative of that in the problem? And we did. You can see that by matching up the colors. The green and the blue is what I'm referring to. Then we make our substitutions. The one thing I didn't include in this problem were the limits of integration because they pertain to x. So this is x equals 0 and x equals 2, okay? Then we just went ahead, like this was just a normal indefinite integral. We found our integral. We made our substitutions. So now I'm speaking right here. We made our substitutions. And then after we made our substitutions, now we evaluate. Okay, so we evaluated the integral, or the solution, negative 1 over x squared plus 1. Between 0 and 2. Okay, and we found the answer to be 4/5. Here's the other way you can do this problem. I'm going to draw a nice solid line. I'm going to leave this zoomed out like this, even though I like to write when it's zoomed in because I think it looks better. And I'm going to come back to this spot right here. The integral of u to the negative 2 du. Okay? Now, I went ahead and I said, okay, we let u equal x squared plus 1. We did that all the way up here. We let u equal x squared plus 1. Well, if we wanted to, as soon as you make that substitution, you can actually change the limits of integration as well. Remember, the limits of integration in this problem 0 to 2 pertain to x equals 2 and x equals 0. Well, why not just figure that out? In other words, what I'm saying here is to do this. For your upper limit, let u equal 2 squared plus 1, which is going to be u equals 5. For your lower limit, you're going to let u equal 0 squared plus 1, which is u equals 1. So now you have new limits of integration, but now they're for the letter u, not for the letter x anymore. Now watch what happens here. We know this is going to equal u to the negative 1 over negative 1, which, if we wrote this out nice and neat, this is going to be negative 1 over u evaluated between 1 and 5. So now when I go ahead and evaluate this, notice I don't have to go back into the letter x because I've already accounted for that when I changed my upper and lower limits. So I get negative 1 over 5 minus negative 1 over 1, which is negative 1/5 plus, well, we know 1 over 1 is 1, so I'm just going to write this as 5 over 5, and I get the same exact answer, 4 over 5. So this is entirely up to you. If you want to, you can always make your substitution back in the x. Let me highlight that so you can see what I'm talking about. I'm going to highlight it in green. So if you want to, you can always make your substitution back in the x, and then you can use the limits of integration for the variable x, and that's fine. Or, if you want to, in blue, you can change your upper and lower limits. You can adjust them to the value of u's. That way you don't have to go back into x. You can evaluate this with your new upper and lower limits, but they're solved for you instead. Regardless, you will always get the same answer. Sometimes it's easier to do this method on the right-hand side of the board, where I put all the stars, because you don't have to worry about as much algebra because you've simplified a lot of this by substituting u. Other times, it's easier to use the left-hand side of the board, where you make your substitution back into x. There is no, hey, here's what you do, and this is why you do it. I mean, it all depends on the problem itself, okay? So let's go ahead. Let's try another one of these, okay? This is turning out to be one of the longest videos of the semester. I wouldn't even realize it. So let's go ahead. Let's try this one. So we're going to do the integral from 0 to pi over 4 of sine x over cosine squared x dx. All right, now remember, and sometimes this helps, sometimes it doesn't, but I'm going to rewrite this as cosine of x quantity squared dx. And the reason why I did that is now I can see, in my denominator, that's a composite function. So we're going to try our u substitution here. So we're going to let u equal cosine x. The derivative of u is going to be negative sine x dx. Now, that negative out front is a constant. It's negative 1. So all I'm going to do is just rewrite this real quick as negative 1 du, or just negative du equals sine x dx, okay? So I can go ahead and make my substitutions because I have cosine x in the problem and I have sine dx in the problem. This negative, eventually I'm going to just move that out front anyways. So when I'm going to rewrite this problem, I'm going to rewrite it as negative integral sine x dx is now going to be du, and then cosine of x squared is now u squared, okay? If you want to, change your limits of integration. I am going to do that here because if you look, right now I have trigonometric functions, so you're going to be using your unit circle a lot and everything. If you change your limits of integration, you actually it turns out you just have like whole numbers or rational numbers or irrational numbers, whatever is the case. It kind of simplifies it a little bit. So for my upper limit, u equals the cosine of pi over 4. Let me write that cleaner. So u is going to equal, for the upper limit, square root of 2 over 2. For my lower limit, u equals the cosine of 0, which means a 1. Okay? So now, let's just rewrite this problem a little bit here. So we got the negative integral from 1 to the square root of 2 over 2 of u to the negative 2 du. Now I'm going to go ahead and integrate. So I get negative, parenthesis, u to the negative 2. When you integrate that, is going to be u to the negative 1 over negative 1. Now remember, this is a definite integral, so I don't have to worry about the plus c. A negative and a negative make this positive, and I'm just going to write 1 over u evaluated between the square root of 2 over 2 and 1. All right? So this is going to be nothing more than just 1 over the square root of 2 over 2 minus the lower limit, 1 over 1. Now we know 1 over the square root of 2 over 2 is really 1 over 1 times the reciprocal, which is going to be 2 over the square root of 2 minus 1. Now what I'm going to have to do here is rationalize the denominator. So I'm going to get 2 over the square root of 2 times the square root of 2 over the square root of 2. Oops, sorry. Minus 1. And that's going to give me 2 square roots of 2 over 2 minus 1, or the square root of 2 minus 1. Okay? So I hope this is helping. I hope it makes sense. All right? If you want to, you can go ahead and do this by making your substitutions for x back in, and you're going to get the same exact answer no matter what. All right? And that's about it for today. So, because I don't want to make this video too long. It's already 52 minutes. But if you have any questions, all you have to do is ask. Just email me. And just to recap your process of finding an integral. So we do have a process. All right? This isn't set in stone, but it helps. 1, try to use the basic rules. All right, like the power rule, or the constant rule, something like that. 2, try to use algebra to simplify. Maybe if you simplify it a little bit, it actually turns out to be a lot easier than what you thought. If these two fail, maybe the problem requires U substitution. Okay? And to do that, you got to make sure you let u equal something. And then you find the derivative of that. And if you could put a check mark next to both of these, then U substitution will work for you. Okay? Now, the last thing I just want to talk about real fast, and it's not, this is very simple. All right? Is there are tables of integrals. All right? And you can use them to your advantage. So, at the very beginning of this lecture, we looked at this problem right here, the cosine of 2x dx. And what we found was the final result was 1/2 sine of 2x plus c. Okay? There are tables that give you this. Let me show you what that looks like real quick. So I'm just going to get out the internet here real quick. Oh, that's what I want. And I'm just going to type into Google here, table of trig integrals. All right, and give me 1 second here. Because I think I went this one. Nope, I don't want that one. All right, here's the one I want right here. Sorry, I had to pause the video and search for it, because this is a really good table right here. So notice you got your basic forms up in the upper left-hand corner. I'll zoom in here for us. So you got your basic forms. You got integrals of rational functions, okay? Integrals with roots, and they're all labeled, different rules and everything. Here's the one I want to look at right here. So integrals with trigonometric functions. So I'm going to just go ahead and snip this real quick, put it into our notes, because I just want you to see it. All right, so we'll put this into our notes. And if you just look at what we have here, the integral of sine ax dx is negative 1 over a cosine of ax. And then if we go back to that table, let's see if I can find it here. There it is. Give me 1 second. Here's our cosine. So there's our cosine right here. Notice that when you have a coefficient in front of the x and it's inside of the argument of your problem, to integrate that, it's 1 over a sine of ax, which is exactly what we came up with. In this case, the a was the number 2. So in reality, if I gave you this problem right here, you don't even have to use U substitution. You can just look at your table and say, well, that's the rule. So it's going to be 1 over 3 sine of 3x plus a constant. There are tons of tables out there. I will upload a table, one that I think is pretty good, and you can use that for your final. But other than that, it's been a great semester. I hope you enjoyed the videos, and maybe I'll see you later on in a different class. I don't think I'm teaching Calc 2 in the fall though. So if you have a question regarding Calculus 2, you can always email me. Talk to you later. Enjoy. Good luck on your final, and have a great academic career. See ya.